online gaming. There are different types of requests coming in, and there is a signal strength for each one. And based on the signal strength and the latency, the bandwidths are allocated, and you can see that the percentage of allocation is done.
Sign into
Okay.
Gmail.
Just look at the set and see the variations in the data set. We have different types of allocations. It can be a video call, it can be a voice call, it can be streaming video, it can be emergency, online gaming, downloading, web browsing. IoT temperature is the different 9 types of data, which are, otherwise you can see that they are repeating. Or 9 or 10 types of data types are available to you. And you can see the signal strength of those calls, requests. You call it as QoS parameters. When a call has been admitted, the signal strengths are those things. And the latencies are the device which is sending IoT is far away from 105 milliseconds it takes to get that temperature. Whereas if you try to take a video call, it is taking 30 milliseconds to get that, which is by the means of latency, you can say that video call is nearer and the IoT is far away, device which is sending and so on. So you can see IoT data, you can see that it is far away, like drone or somewhere. And video call and voice call, you can see that they are from mobile user who is nearby to the base station. Only the IoT temperature is far away, which is like a drone or a HAP or somewhere it is lying. Based on the latencies, you can tell them. And the requirements, if you try to see, the minimum bandwidth required is for IoT temperature only, where the data set is very small. And the highest will be for video streaming or video call. Sorry? Emergency service also needs bandwidth, but it is not that high as video streaming and all. Right? You can see the video call takes the highest bandwidth. Right? So lowest will be the temperature sensor. So of all the group of video calls, if you try to see, only 70% is allocated to video calls and so on. You can see at that instant what it is. So this is the data set which is in your hand, and now we move on to the codes. So you can see that you can, the important thing over here is the first line. If you try to see, there are 3 important commands you have to give at the beginning. Import, pandas 1, numpy 1, re1. These 3 are important. You have to write for all the codes, right? And then you have to write model, sketch, assemble, pre-processing, and a plot. Okay, my plot you have to use for plotting the waveforms. And you are uploading the data set into the Colab your directory, and then you are loading the data set, remove the special characters in the columns. Then you read the signal strength, latency, allocated bandwidth, and the resource allocation. And then you try to train the machine learning algorithm, and you have you are training with random forest model. And random forest is very good in case to find out any discrepancy in the data set. right? If you have any deviations from the data set, actual data set, that can be easily detected by means of random forest algorithm. Okay. So using that, you are trying to find out the absolute error, R-square score, and accuracy of the algorithm and the outcome, and then you are trying to so now the accuracy of the algorithm depends on the data set. The larger the data set, it becomes more accurate, right? So here if you try to see, you can see that video call, voice call, streaming, emergency, online gaming, you have different types of application. You can enter one application like voice as video call. Minus 60 or 70 you can get. Latency 10 milliseconds or so you can predict that this much resource is required if you have video calls around how many video calls you have given? Not video calls, which is the number of bandwidth units you are allocating to video call is only 10. If you allocate that much, you can see that resource is 72% resource have been allocated to it at that latency and that bandwidth. So now the total resources with you, you have to allocate for drones how much, for phone calls how much, for videos how much, for gaming how much, all these things you can distribute it and you can allocate it. Right? So you can see the allocations and you can vary the interest also. Right? If you want to allocate more for sensor data, you can pick up sensor data and you can give larger bandwidth for it if you have too many sensors and all. Right? So now please try to look into it for some time. We will give you the next algorithm. Okay, you can just go to the Colabs and get the decision tree algorithm given to you. No, you can kill him. No, algorithm. Yeah. So now we are trying to run the decision tree regression algorithm. So basically what we are trying to do is we are trying to form a tree and of the applications what we have like video call and so on. We are trying to divide into two subgroups and so on and going up to the root node, and then we are trying to make a decision on it. So the sets from the given 11 or 12 set, we are dividing into 50 and 50 and then again 50 and 50 and so on. So which means 5 and 6 on one side and 5 and 6 and so on until we get the last decision node. So then we are applying the prediction algorithms and trying to predict the model out of it. So now we will try to run this algorithm for the same set and we will try to see. So out of the 12 services what we have, you can see that one of the service was actually 60% requirement was there and the actual is also 60%, whereas the other one if you try to see, we have different resources requirement for 55, 65, 70, 75 and 85, but actually the allocated one is only 70. So you can see that the actual allocation and the predicted allocations are almost matching. It has matched with the 6 of the outcomes than the 12 out of it. Okay. So you can apply for streaming if you try to see. Signal strength of 70 if you take it, and latency is around some 12 or 25 you can take it. So allocated bandwidth will be some 50. So as you can see that the values what we have taken are and the training set are not same. Right? The training set what we are given to the machine and what we requested are not same. So there is a small change in that. If you try to see the so the streaming, in the earlier case it is written 2 Gs I think. Yeah, okay, 70, and the latency is around 25 or 20, and the allocated bandwidth is 5. So with 85% you can accurately predict the values, right? So when you are trying to pass on these values, it should be realistic in nature. You cannot give some arbitrary numbers and try to ask the algorithm to predict it, right? Close to the actual values you are supposed to give it. Okay, and you can just see for different services like voice, video and all, you can just manage to see if you are trying to use video services on your drone, so the latency values will be very high. So you can increase the latency and see whether it is predicting accurately or not. Can we move to the next algorithm? So we are moving towards the yeah. So now we are trying to move towards the gradient boosting regression algorithm. So there is a model called as gradient boosting algorithm model. we are trying to use that directly the model, and we are trying to. So there are, if you try to look into the ML, there are a number of models which are already existing. You can use them to basically start with, and once you have a grip, you can change the parameters and requirements for your application. So if you are trying to look for the data sets, you have a lot of data sets available in Kaggle. And the Kaggle, you have a lot of data sets where you can download. Otherwise, you can generate a synthetic data also. It is not that you have to download and do it. Based on the experiment, you can generate a data set and you can use it also. Taking a long time. So now let us try on emergency services and see what it has. $70, 10, 30 or 40.
10 kbps to 15 mbps.
Yeah. Yeah, so with more accuracies you can predict, because it's emergency service, top priority will be given for that. And even the allocated bandwidth units, if you give more, it is fine. But since very rarely you get an emergency call, it is not that all the calls will be emergency. So we'll stop with this. You can work. Works what we have done. We will just try to put it up. So one is last year we have done, before last year actually we have done one machine learning algorithm has been developed to predict the age-based risk, if he is hypertension or if he is having obesity or if he is having some heart trouble, all these things taken into consideration. We can predict that what is the risk of a patient. He has to give his weight, his body mass and his height, all these parameters if we pass on, he will get the prediction whether he expected to get heart attack or he is able to get some of the parameters. And for that we got a best paper award also in IEEE TENSCON. And there is another work what we have done is resource allocation over a bandwidth constrained linear vehicular networks. And this was also presented in IEEE Bangalore, some conference name I have forgotten, but it is there also we got a good response with this paper, where we have taken only a linear network. We don't have multiple roads and all. And there is another algorithm which we have presented in vehicle to network resource allocation using Q learning and random forest. And there also we got a best paper award for that. And here, especially in this, we have used two learning algorithms cascading one top of other and trying to use for better allocation of resources. And there was another project done by one BTech student only from Kids College, I think. He has done He is actually third year student who came for summer interns, and he has spent 2 months on this. And we also presented this in IEEE ISS, and there also we got a good response for this. So here there are like a lot of gas sensors and smoke sensors in the colony, and whenever there is smoke or something, it has to detect and inform the fire station so that they'll come and put it off. The other one is this is again a payload allocation only, which we are trying to use to maximize the efficiency of a network. So this is one more work which we have done, and this also has been published in the IEEE journal paper. So these are some of the works which we have done last year, not this year. This year we are supposed to get some more, and that is on the microprocessor front, machine learning front.